Yeah, hi folks. This is the next video for the Further Maths Pure. Must be pen. Where is it? There it is. I'm going to split this into two. We're starting chapter 9. And we're going to start looking towards 9a. But there's just a few things I want to, a few concepts I want to talk about before we start looking at the examples. It starts off with looking at the equation of a straight line. Now, here's the equation. Here's a straight line in 2 dimensions. Seen this a billion times. Let's say it's y equals 2x plus 5. Now the way we've talked about this before is we said, so the line is any position on the line where this relationship between the x and y coordinates is the same. It is true. I want to think of it slightly differently. What I want to say is, I can get anywhere on the line by starting at a point and going in a particular direction. Specifically for this line, I'm going to start at the point 0, 5, and I can go any multiple of this direction and I'll stay on the line, because of course a multiple of this direction could also go in that way if it was a negative multiple. Now let's be more specific about this. I'm defining the line by saying, how do I get to any point on the line? So I might say, go to 0, 5, and then add any multiple of the vector which follows the direction of the line. Any multiple of the direction vector. And in this case, it's got a gradient of 2, so of course that means you go along 1 and you go up 2. So along 1 and up 2. And we've seen vectors at GCSE before, so we're aware that across, or the x direction is the top and the y direction is the bottom. Let's just work on this equation, this description a little bit. The position vector, I don't know why it's half a position, but it is, the position vector of anywhere on this line can be got by taking the position 0, 5. Now that's just writing the coordinates as a vector. It means from the origin go 0 in the direction, in the x direction, and 5 in the y direction. And adding on, and I'm going to use the Greek letter lambda, adding on a multiple, any multiple, of the vector 1, 2. This is the vector equation of the line. It's the same line, but instead of just describing it as the relationship between the x and y coordinates, I'm describing it as a position on the line and the direction of the line. I can get anywhere on the line by going to 0, 5 and adding on some multiple of 1, 2. So this is a vector equation of the line. I could get another vector equation of the line by changing my point. This is the same line. That would work, wouldn't it? These two lines are not only parallel, they're the same line. So this is, as long as it starts with any point on the line, they'll all be the same line. So there's an infinite number of vector equations of this line. Now it so happens that I've described this line, this 2D line, as a vector. But of course I can describe a 3D line as a vector in exactly the same way. So, the vector equation of a line can be written as r equals a plus lambda b. Notice lambda's not a vector, lambda's a scalar, where a is a position on the line or a point on the line, and b is the direction vector of the line. And it doesn't matter if A and B are 2D or 3D. So, for example, let's say a line might be, I don't know, 2, 5, 7 plus lambda 3, 9 minus 1. Now, at some point, we need to be able to convert between the vector equation of the line and the Cartesian equation of the line. Let's not go there quite yet. Well, we'll do that. We need to do that for 9a, but let's not go there quite yet. So the vector equation of a line can be defined as a position on the line and the direction. Now I've used lambda. We might use, the characters you're going to see are lambda, mu, and often t if I need a third line, but normally mu and lambda. Okay, so let's do, I'm going to do example 1 and 2 in this video, and then I'll come back and we'll look at 3, 4, 5, 6. So, example 1. Find a vector equation of the straight line which passes through the point A. So A is point 3 minus 5, 4. Now, in the example, they've actually given A as a position vector, 3i minus 5j plus 4k. And I think I'm right in saying you've seen this in your mechanics before. This is the x direction, the y direction, and the z direction. Whenever I see a vector like this, I write it as a column. 3 minus 5, 4. So this is written as a set of coordinates. This is the location. This is the position vector of that location. It's how to get there. So they do have subtly different meanings. Okay, so this is my position. This is the position on my line. And it's parallel to, so the direction is 7i minus 3k, which of course is 7i 0j minus 3k. So position, or I should say position, direction, the line then, the position vector of anywhere on the line is the position vector of my starting point plus any multiple of 7, 0, minus 3. That's it, done. If you want to, it might be more convenient at times, you can write it as a single vector. 3 plus 7 lambda minus 5, 4 minus 3 lambda. They are identical, there is no better or worse. I'm going to do example 2 in this one as well, aren't I? Example 2. example 2 says, it gives me the 2 points. It gives me point A, which is 4, 5, minus 1, and point B, which is 6, 3, 2. So I've got my line. I know it's 3D, but I'm just going to sketch it on 2D axes. I've got A, and I've got B, and of course I need the direction. The line goes through A and B. Now, find a vector equation. That's because all I need is a position. I can use either A or B. Remember, these are not position vectors, they're coordinates. The convention is a position vector is written in lowercase. So the position vector for point B is lowercase b. Okay. The position vector can be A or B. I'm just going to choose A. It doesn't matter if we do or not. I need the direction part. And the direction part, of course, is just the vector between A and B. So if the position is 4, 5, minus 1, the direction, well, that's vector AB. How do I get from A to B? And I can just say, how do I get from 4 to 6? I add on 2. How do I get from 5 to 3? I subtract 2. How do I get from minus 1 to 2? I add 3. So that's my direction part, which means the line is defined by the positions that you reach by starting at 4, 5, minus 1 and adding on some multiple of 2, minus 2, 3. There's an infinite number of equations for this line because I could have said 6, 3, 2, add some multiple of 4, minus 4, 6, because of course they're parallel. And as long as the direction is the right direction, it doesn't matter how I write it. Generally, I try to simplify this, but that they are equally correct. They're the same line. Of course, if I wanted to work out values of lambda, then it would matter where I was, but let's not go there yet. Okay, so that's example 1 and example 2. I'll do the next one with 3, 4, 5, 6.